Okay, so hello again. I'm back. So now I'm on the third module as promised. So this is all about stoichiometry. This is where we'll be trying to solve uh, some problems regarding chemical reactions or chemical equations. But on a basic level, of course, more advanced videos or more advanced skills will be tackled on other videos. But for now, this is really an introduction to stoichiometry. So when you talk about stoichiometry, so what is it? So it actually comes from two words. Let's get that going. So it comes from two words, stoichio, and of course, metry. So stoichio means element. It's a Greek word which stands for element, and then metry. You know that already. It's a very common term. It stands for measurement. So what do we do in stoichiometry? It is about measuring the amounts of elements and compounds involved in the reaction. If you really want to understand uh, the nature of the reaction and get, of course, probably when you want to analyze why this element is combined with this element, why only this amount of element needs to be combined with this element, that is stoichiometry, where you will be solving masses, ratio, moles of different elements in different compounds. Okay. So stoichiometry can be applied by using different variables. First, for example, this one, you can actually solve problems just by having the number of moles, probably an atomic mass unit, or the amount of substance or given mass. So let's say, for example, water, when you have two molecules of water, because you can see from here, when we talk about molecules, in two molecules of water, there are actually four atoms of hydrogen and two atoms of oxygen. Sorry, but that's two, and then the product is two molecules of water. When we're talking about mass, we said a while ago, I mean in the other module, that mass in terms of AMU and mass in terms of grams are interchangeable. They're actually the same because you actually rely on the atomic weight or the atomic mass of the number. So here you go. For example, here, since we know that H has a weight of 1 gram, so in two molecules of water, H has 4 grams, and then oxygen has 32 grams. When you're talking about moles, it's different. So in 2 moles of water, there are actually 2 moles of hydrogen and a mole of oxygen. So these are some ways to represent your stoichiometric reactions. So not every time you get a problem wherein everything is given in mole, it could be mixed. Some will be given in grams, some will be given in moles. So always remember though that in analyzing a chemical reaction, you always have to start with a balanced chemical reaction. So how do you do that? In this is a block diagram what you can do. So let's move me a little. So for example, given grams of substance A, we can actually use the molar mass of A and then moles of substance A, and then probably get the coefficients from the balance equation. You get the moles of substance B, use molar mass, and finally, you get the grams of substance B. It's always important to understand the importance of a balance equation because that's where you'll get the molar ratio of each element in that compound. That's very important that it is a correct and it is a balanced chemical reaction. Okay, for empirical formula, this is a very common term that we hear every now and then when we're balancing equation. Empirical formula is simply the smallest or simplest formula wherein you'll be using the smallest whole number mole ratio of the elements. So, for example, in this case, wherein you have hydrogen peroxide, the formula for hydrogen peroxide is H2O2. As it is, of course, this is the common ones. This is the formula that we use for hydrogen peroxide. But if you want to get the empirical formula of hydrogen peroxide, then you have to get the smallest whole number and then divide it. It means this is actually the empirical formula of hydrogen peroxide. It says there, if the two formulas are different from the molecular formula, will always be a simple multiple of the empirical formula. Yes, that's true. This is actually a multiple of the empirical formula of hydrogen peroxide, which is HO. And then it says here, if the percent composition is given, you can always assume that the total mass is actually 100 grams and that the percent by mass of each element is equal to the mass of that element in grams. You can always use over 100 as a basis, like just to get the percent composition. You always assume that together they make 100%. So you can use 100 grams as a reference. The mass of each element can be converted to moles by dividing the molar mass of the element. For example, in this case, for sulfur oxide, that's SO. Okay, so in this percentage, the percent composition of sulfur oxide is 40.05 sulfur and 59.95% oxygen. So I'll just get my pen tool so that I can like write notations. So what do we do? We're getting how many moles of each are there in this compound of sulfur oxide. Okay, so you use the percent composition, and then this will be, of course, the uh, formula weight or the molar weight or the molar mass, and then you can just divide it, and then you get 1.249. So that's how many moles of sulfur there is in sulfur oxide. Then since this one has a greater percentage, but of course you get the molar mass of oxygen, which is 15.99, or sometimes in other references it's 16, then you get it. And then when you begin to compare it, when you want to get the ratio, which of the two are you gonna get? Are you gonna get this or are you gonna get this? You always choose the one with the smaller value. So you're using 1.249. In doing that, you can actually get the number of moles in whole numbers. So 1.249 over 1.249, that's 1. And then good thing, this is 3.749 divided by 1.249, that's 3, which means there is a 1 is to 3 ratio of sulfur to oxygen. So it means for every 1 mole of sulfur, there are 3 moles of oxygen. That is how it is based from the molar weight or from the molar mass and the percentage composition of sulfur oxide. Okay. So in short steps, it's good to know the percentage to mass, mass to mole, and then divide by smallest and multiply until whole. These are short steps that you can do when you're trying to apply the empirical formula, when you're trying to analyze chemical reactions. But let's have more examples with regards to stoic and short examples that would help you understand it further. So, for example, in this, I have a reaction here. It's 4NH3 plus 5O2 yields 6H2O plus 4NO. So, it's important to understand the mole ratio. So, where will you get them? You will get them from the coefficient. So, 4, 5, 6, 4. At this point, you may not realize the importance, but these are very important when you're trying to solve molar ratio, masses, number of moles in a reaction. So, how do you read this or how do you interpret this? It means that 4 molecules of NH3 reacts with 5 molecules of O2 to produce 6 molecules of water and 4 molecules of NO, or change molecules to moles. 4 moles of NH3 react with 5 moles of O2 to produce 6 moles of H2O and 4 moles of NO. So interchangeably, you can actually use moles and molecules because that is actually the different parts of that chemical reaction. 1 mole, 1 part, 1 part. That's how it is. In this case, it's a 4, 5, 6, 4 mole ratio. So let's start with example 1. How many moles of water are produced if 2 moles of O2 are used? Though it's already, you can already see the solution here. I'll just redo it so that you can understand it hopefully better. So, but pardon my handwriting. So it says here 2 moles of oxygen. So we're looking for how many moles of water are produced if 2 moles of oxygen are used. The technique for me would be to get the given and highlight the ratio. Oxygen, where is it? Oxygen, that's 5. And then water, that's 6. So I start with 2 moles. So even if I don't look at that, for example, I have 2 moles of oxygen multiplied 2. You know that for me to cancel moles here, I have to put moles here. So moles of oxygen also. You can see here, you just get the reaction. You get the ratio. What is the ratio? That's 5. And then, of course, you're looking for the moles of water. So, how many moles of water? You have 6 moles of H2O. Therefore, the answer is 2.4. Same. Just for you to understand it further. Where is it coming from? It's actually coming from the molar ratio at the initial reaction. Okay, let's have another one. For NH, same reaction. How many moles of NO are produced in the reaction if 50 moles of water are also produced? So check. What do you check again? You check what are the given water and NO. So water 6, NO 4. And it's very evident here. Okay, write the given. The given is actually 50 moles. That would be the trigger point, and that will be the first thing that you have to write because that's already a given. You don't have to solve it. So that's 15 moles water. And then for you to cancel water, it's here. 6 moles, it just came from here. And for every 6 moles of water, you have 4 moles of NO. There, that's 10. Very simple, right? So that's why it's very important to uh, have a balance equation and make sure that your balance equation is correct and so that those coefficients are also correct because they're very important in problem solving. What about this one? How many grams of water are produced if 2.2 moles of NH3 are combined with excess oxygen? So what is given? You're looking for water. So water is 6 and then NH3 is 4. So I have to see that fraction or that ratio somewhere in this formula. There you go, 6 and 4. So what is given? Are produced if 2.2 moles of NH3 are combined. So 2.2 moles is given. So cancel that. So that's 4 moles of NH3 has 6 moles of water. And then where did I get 18.02 grams of water? I get it as this smaller mass. So let's check, let's validate. How did we get 18.02? It's coming from the periodic table. So oxygen and then hydrogen. You have 2 hydrogen atoms and then you have 1 oxygen atom times. You go to your periodic table. Let's check the um, masses. Let's keep those annotations. Okay, let's open a periodic table. So we're looking for oxygen. Oxygen is 15.99. So let's go to our PowerPoint again. So let's write that here. And water is, let's get water as well. So we're, by the way, if you can see that it's here, here is 15.99 for oxygen. And, oh, what did I say? Did I say water? I'm sorry. What I mean is hydrogen. For hydrogen, let's look at the exact value. Hydrogen is 1.008. So let's go back. So hydrogen is, excuse me, it's one. Okay, hydrogen is 1.008 and this is 15.99, which means this is of course 15.99 and then 2 times 1.008. I'm just going to get a calculator because, just to be exact, that is 1.008 times 2. That is 2.016, adding them together, plus 15.99. I get an 18 point. I have an 18.006. Probably this reference used another book or another, or rounded off to the nearest. Okay, and then you get, just multiply everything And then there, approximately get 59 grams of water. So that's very simple. Okay, let's go to the next one. How many grams of O2 are required to produce zero point 0.3 moles of water? You can see here. Checking it again, we're looking for O2. So O2 is 5, and then water is 6. Therefore, you should always find a 5 is to 6 ratio on your equation, your working equations. 5 is to 6 ratio, zero point 0.3 moles, 6 moles of water per 5 moles of oxygen. And oxygen has a 32 molar mass, so that's 8 grams of oxygen. And finally, for example 5, how many grams of NO is produced if 12 grams of O2 is combined with excess ammonia? So NO, that's 4, and then O2, that's 5. So you should be seeing a 4 is to 5 ratio, which is this one, as you can see from there. And then just plug in the molar masses and you're getting 9 grams of NO. That's how simple stoic is. So it's not really a complicated process as long as you remember things like the proper balance equation, the correct balance equation, the proper ratio. Because if you don't have if you don't have the correct balance equation, then you can't get the proper ratio. And then um, identifying the correct masses from the periodic table. Okay, for on my end, you can actually use the two decimal places and will still be um, very near the answers. Okay, okay. This is just some important notes. We always use the same type of information to make the jump between steps. Uh, all you have to remember, as I've said, is make sure that you have the correct information at the onset of the problem solving, so that later on, when you're beginning to plug in values, they are correct. Okay. Okay. Let's have this example. 4NH3 plus 5O2 yields 6 water plus 4NO. Okay, I don't have this, doesn't have a plugins already, so let's start. But give me a moment, I'm just gonna, oh wait, let's keep those annotations. I'm just gonna copy it so that we can have it, I can have blank pages. Okay, let's have this one. Okay, there you go. Okay, the first question is how many moles of water can be used using 1.6 moles of NH3? So I'm just gonna get a pen tool. Okay. So I said always refer to the statement, what is given. So you have water and you have NH3. So how many? The water ratio is 6. And then NH3 is 4. So you have to start with this. So this is your given. So 1.6 moles of NH3 multiplied 2. We're looking for the moles of water. So get that ratio, that molar ratio. So NH3 is 4 mole NH3 and 6 mole water, right? And then we're still not finished. Okay, that's it. I believe so. Because we're just looking for the moles of water. So let's cancel this mole of NH3. And then that's it. How many moles? We're just looking for that. So that's 1.6. Just give me a moment. Times 6. So the answer is actually 2.4 moles of H2O. Okay, this is for the first problem. Okay, what about the next question? Okay, I have it here. I did not I did not delete them anymore. So what mass of NH3 is needed to make 0.75 moles of NO? So looking at that again, It's NH3, so check that. And then NO. So there you go. And then what's given is 0.75 moles of NO multiplied to, we're looking for the mass of NH3. So this is mole NO. So that's 4, right? And then for every 4 moles of NO, we have 4 moles of NH3. But that's just the moles of NH3. It's not the mass of NH3. So you have to get the molar mass of NH3. Okay, what is the molar mass of NH3 per, what, oh yes, because we need the mass. So NH3 and H3. Okay, we know that hydrogen is 1.008 times 3. What about nitrogen? Let's see. I'll just Google it so that I don't have to switch windows. Of nitrogen. It's 14.00. So that's 14.00 times 1. So approximately that's, of course, 17. So all you have to do is you have 17 grams per 1 mole of NH3. So the answer is, so let's compute that. That's 0.75 times 17. Oops. That's more or less 12.8. So that's a 12.8 grams of NH3. So that's how you solve it. What about the last question? Okay, let's go to this. The last question is how many grams of NO can be made from 47 grams of NH3? So check that again. That's NO, that's 4. And NH3, check that, that's in there. I guess it's the other way around. It's very similar to letter B. So what are we doing? So we put 47 grams NH3 multiplied to, we said that NH3 has 17 grams per mole, right? Oh, sorry. Why did I do that? Let me erase that. Sorry. I talking to myself and writing at the same time. So there you go. That should be there. Let's get my pen tool. Okay. So it's 17 grams per mole. There you go. And then that's NH3, right? So for every gram of NH3, for every mole, you have 4 moles of NH3 and then 4 moles of NO. So that's it. So let's compute that. It's 47 times, or I'm sorry, divided by 17. Our answer is 2.76 grams. Okay. So basically, that's how you do your problems with problem solving for stoichiometry. These are basic problems, and this is just an introduction to uh, more complicated problem solving for stoichiometry. But at least you have an idea on how to convert molar masses, how to apply the ratio, and you have to also understand that it should always be a balanced equation. Let's first check the last one. How many grams of NO? 47. And then, that's correct, right? 17 grams per mole. And then, okay, this is just the most. Okay, I think I missed something. Let me just do that again. Because I don't think that's grams. It's too little. Okay, here we go. I think that's just most. I'm not yet up to that point. Okay, let's go back. 47. So cancel that moles. This is just moles, not yet grams. So we have to get the NO, molar mass of NO. So we know that one is 14 and the other one is 16, right? So this is, for every mole of NO, you have 30. Okay, 30 grams per mole of NO. So where did I get 30 from NO? Oxygen is around 16 and N is around 14. So that is 30. So let's multiply that because I just detected that it's too small. The number is too small. So let's compute that. So I don't have ready-made answers, so I'm just computing. 47 times 30 all over 17. So the answer is around 82.94. Okay, there you go. That's more like it because 2.7 was too little. I just noticed. Okay, so for now, that will be all for our lecture on stoichiometry. So I will have another set of videos for examples using more difficult examples or more difficult problems. Okay, so please stay tuned. And again, please like and subscribe the page so that you'll be updated whenever there are new videos available. Okay, so that's it. So happy reviewing. Bye bye.